Syzygy episode 69, Solar Secrets and Nebulous Neutrinos. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart. I'm in York, not in York, but sitting on the other side of the Zoom call from me, Dr. Emily Brunsden. Emily, you're across the other side of the country, but still part of the show. Good to see you.
Hello, hello. Oh, yep, my microphone was just about to roll off the pile of books. I was like, oh no. But it's okay.
This is the danger of ad hoc podcast recording, as I'm looking at Emily on the Zoom and she's got the microphone balanced as usual on a tall pile of academic texts. What are we reading today in the podcast, Emily? What's on the pile?
So we've got stellar spectral classification.
Very nice.
That, top 10 hit.
Yeah. I'm waiting till they make the film, frankly. What else? What's on there?
So we've also got Communications and Astroseismology, user manual for Fummius and Das.
Nice. Well, that's, that'll keep us going through the rest of this pandemic lockdown. Very nice. And how you been? You keeping well?
Yeah, going not too bad. I'm waiting for the sunshine. This British summer is getting a bit tedious.
I think a lot of us are waiting for the sunshine. And in fact, that's a relevant point. I'll try that word again. That's a relevant point for one of the little pieces of sort of newsy podcast starter that I thought we'd mention today. There's a couple of things before we get into our subject of choice. And I should mention what that is. Today, we're going to be talking about the sun. And the big jigsaw puzzle.
And how it shines.
The big jigsaw. There's so many links. My God, I didn't even see that one coming. There's so many pieces of the jigsaw puzzle about how the sun works, what it does, where the energy comes from, all the nuclear stuff that goes on inside the sun. And we think, maybe, we really hope that the last piece of that jigsaw puzzle has been experimentally put in place. It's been confirmed. Observations of neutrinos coming from a very specific part of the solar fusion process, which is very exciting, particularly as it happened in a big liquid-filled balloon a mile underground in Italy. But we'll come to that in a minute. Before that, Emily, have you seen the comet?
No,
you haven't seen the comet. And there's a couple of reasons you haven't seen the comet. And we're talking about Comet Neowise. I think that's how you pronounce it. That's how it's spelt anyway. Comet Neowise, which is in the skies at the moment. And it's been in the news. I've seen it in the news. There's been pictures. There's been news articles and reports about it. Big comet in the sky. Very exciting. Go and see it. Unless you're in the UK, in which case it's been cloudy for a blummin' fortnight and you can't see anything anyway. So that's one reason that maybe, Emily, you haven't seen the comet. I'm assuming you haven't seen Comet Neowise. Have you spotted this one?
No, I haven't spotted this one. And you're right. I mean, it has been very, very cloudy.
Yeah, crazy
But on
cloudy.
the bright side, it's not all lost just yet. We've got maybe a couple of weeks to try and get out there, and one would hope that in that time to spot it, we can have some clear night skies.
One really hopes.
So the comet, it's just been past the sun, so it's just been on its closest point to the sun, and it's now coming sort of back out, and it's coming back towards the Earth. So that's why we sort of say, well, from now on is a good time to have a look at it.
And if you can get a clear view of it, it's, there's some really nice pictures out there. And yes, okay, you can't always believe everything you see on the interwebs. Maybe that camera's been pointing at that comet for an hour and a half to collect that beautiful picture. Maybe with the naked eye, it's not quite as clear. But all reports are, it's supposed to look pretty cool. Just before sunrise, just after sunset, over on the horizon, if you're looking from the UK. If you manage to get a clear bit of sky, it's worth going and having a look for. It's not very far from the Big Dipper, I think, or what do you call it in this country? The saucepan or something? The big spoon? I don't know what you call it.
Yeah, no, I think it is a Big Dipper.
Yeah.
So it's in the northern sky. It is quite close to the horizon, so it's worth making sure that you can't that you can see it, that you can't it's not all blocked by trees and houses and whatever.
Yeah, get up somewhere high. Go climb a ladder or something.
And it's going to be almost due north by about the 15th of July. So
right.
One way to spot it would be to look north-ish, look at the Big Dipper, and sort of follow where the Big Dipper's tail is pointing, but pointing through the scoop, if that makes sense.
Yeah, follow that down through.
Point through the scoop down to the northern horizon, and it will be roughly around there.
And with any luck, you'll see a bit of a comety smudge, and you can say, yes, I have seen Comet Neowise, which is better than Emily or I have managed to do until this point. That's not the only thing in the news at the moment. Before we get onto the big sun-related stuff, Emily, Mars. We're going to Mars, and we're going to Mars very soon. And by we, I don't mean people. I'm not going, you're not going, but something's going. What's happening around Mars?
Well, 3 somethings are hopefully going to launch in the next few weeks to head to Mars.
Yeah, what are they?
Well, we've got 3 different nations who are launching Mars missions. So this is very exciting. So we've got the US who's launching their long-awaited rover Perseverance.
Yes. Yes, this was the one where they had the online competition to come up with a name, and staggeringly it didn't come back as, Marsy McMars face. It came back with Perseverance, which we had a bit of a discussion at the time, and I kind of like it. I think, Perseverance
seems more relevant now, doesn't it?
It does, rather. Come on, we can do this. We can make it. All right, so that's America sending another rover, which is good. I'm assuming this is sort of an upgraded, the ones that are already on Mars, wandering around doing their thing, but this is sort of upgraded with extra tech.
Yeah, it's got a little bit of a drill, so it can drill down into the Martian surface. But one of the big goals is to take some samples from Mars and put them in little kind of hidey hole boxes that one day we hope with another mission we can go and collect and bring them back to Earth.
That would be very cool, because we've never done that before. We've never done the collect and return thing, because, from space, that's one thing. But from Mars, that's a really, really different proposition. I don't know that we've ever come back from Mars yet, have we?
No, we haven't,
No, so that would be very cool. Okay, so that's America. Who else is going?
So the UAE, the United Arab Emirates, are sending a mission as well. So they're sending a orbiter.
Mm-hmm.
And the orbiter is called Hope.
Perseverance and Hope, I like it. The UAE, do they have a big space program? It's not one you hear about a lot. I'm a bit surprised that the first time I hear about it, they're going to Mars. That's ambitious.
It's very ambitious. So they didn't have one until about 6 or 7 years ago. But I think they put a lot of resources into pulling together some former NASA scientists, but then also there's a lot of really clever young people in that part of the world who have put together a scientific community that's very, I think, creative and ambitious. So it's an interesting mission. It's going to be quite fun.
That's very cool. I like the sound of that. Okay, so that's 2. We've got a rover. We've got an orbiter. What's number 3?
Number 3 is China's mission to Mars.
Mm-hmm.
Now, China is probably the most ambitious out of all 3. Now, you might remember...
They're sending an entire town.
Well, so China did have an attempt to send a mission to Mars in 2011 that didn't work.
Didn't work. At what stage did it not work? Did it get off the ground?
I don't recall the details. I don't recall, but it was, kind of 0 for 0, 0 for 1, if you like, for China, for Mars at this point. So I think it's incredibly ambitious that they're sending an orbiter, a lander, and a rover in 2020.
Wow, they're not mucking around. We are definitely going to Mars, come hell or high water. Well, and these are all launching when? Within the next couple of weeks?
So the Chinese one. Well, we've got to go with the name. So the Chinese one is.
Because the name's important. We've got Perseverance from America. We've got Hope from the UAE, and from China,
Tianwen-1, which means Quest for Heavenly Truth.
Wow. Okay, it's Perseverance, Hope, and Quest for Heavenly Truth. I think the Chinese are winning this one on the naming stakes. If you're going to go, then go big, I reckon. Well, good luck to all of them.
Yeah.
We'll be watching with great interest to see how those launches go.
Yeah, so they've got to go in the next kind of few weeks because this is the window of opportunity whereby it's easier to get to Mars, basically.
Right. Yeah, you get the timing wrong and you've got a hell of a long way to go and a lot more fuel you got to take and all of that sort of thing. So now's a good time. Good time to go to Mars.
And it's amazing that even with a pandemic disrupting the final few months of preparation of all these missions, that they're all ready to go and they're off.
I guess there's nothing focuses the mind like an interplanetary window.
Yeah, well, maybe it just sort of says, well, the Earth's not looking super great right now. Let's push on that.
We
mission
really
to Mars.
need this one. We really need this one. Come on, everyone, let's go. Well, good luck to everyone involved, and we look forward to seeing how that one turns out. We'll report back in future episodes and let you know. It's going to take a while for them to get to Mars, though. How long does it take to get to Mars if you're in a spacecraft?
A few months, so they'll be there February-ish next year.
That's a long way. There's no way in hell you would get me on a spacecraft going there on the first manned mission. Not a chance.
No, you should hear me moan on long-haul flights. I mean,
It's bad enough going to New Zealand on 24 hours, let alone Mars. Anyway, enough of that. Let's get on to discussing the sun, Emily, because some really interesting news very recently. Out of a very deep mine shaft in Italy, there's been reports of neutrinos. So talk to me about this story. We're talking about how the sun works, how the nuclear processes way down in the core of the sun do their thing. And it's very, very complicated. It's not just sort of taking a bit of hydrogen and turning it into a bit of helium. There's all sorts of stuff going on down in there. It's very, very complicated. But I'm going to ask a very, very simple question here, which is, I kind of had the impression that we'd already sorted all of this out. I thought that the sun was really, really well understood and sorted out and experimentally confirmed. And so I'm a bit surprised when you send me this Nature paper that says, well, we've finally put the last piece of the puzzle in. What's going on, Emily? Correct me if I'm wrong.
well, you're sort of right, because that is true if you compare it to any other star that we know in the universe.
Right.
We know far, far more about the sun and how it works. I mean, orders of magnitude more than anything else that we've managed to observe.
That makes sense because the sun is orders of magnitude closer to us. It ought to be really well understood. I was just surprised that, well, there's this process that we understand is going on down in the center of the sun. We can talk about what that is. But we've only just found the experimental bit of the puzzle that fits with that. I find that absolutely staggering. So there's some really good stuff going on here. Let's wind it back. Emily, who are we talking about? What's happened? Where? And why?
Right. So this is, I guess, in some ways, a nice sort of pandemic piece of research that's happened. Now, the research itself is not related to the pandemic, but the announcement of this discovery was made in a virtual conference. It was called the Neutrino 2020 conference. And the announcement was made by the team which run an experiment in Italy called the Borexino. I might not be saying that with quite the correct Italian emphasis, but
apologies to Italians everywhere, but it's close enough.
Yeah, so there's a group. It's a team of people who have this big neutrino detection experiment. It's been running for quite some time underground in Italy, and what they were able to announce at this conference is that they have detected for the very first time neutrinos coming from a series of reactions we call CNO reactions in the sun. Fusion reactions.
CNO. Now I've heard of the CNO cycle. CNO cycle, is that the right terminology?
Yeah, that's right. Same thing. Yeah.
Yeah, and if you've done any sort of basic high school level chemistry, you might be able to guess what the C, the N, and the O stand for. It's carbon, nitrogen, and oxygen, right? It's a cycle involving carbon,
That's
nitrogen, and oxygen. So give us a little bit of a rundown on what's happening here. What's the process?
Yeah, so CNO is a really important fusion reaction in stars, but it's not a very important fusion reaction for our sun.
Okay, so it's for stars in general, but not our sun?
That's right. So our sun is kind of at the very, very tail limit of even having this reaction. But if you go to much, much bigger stars, then this becomes the dominant fusion process that's producing all the heat and light that were from the stars. So any star that's bigger than kind of about 1.3 times the size of our sun, pretty much all that energy is generated by this CNO cycle.
Wow, so it's that important, just not in our local area, not in our local environment.
But the sun's kind of, it's only got less than 1% contribution to the energy output of our sun.
Right. Okay. So that explains why. I mean, I've certainly heard of this process before, the CNO cycle, but it also kind of explains why in this particular discovery, it's such a small part, such a tiny fraction of what the sun is doing, that this starts to kind of make a bit of sense as to why it might have taken a while for this last piece of the puzzle, the experimental puzzle, to be put into place. The thing I find really interesting about this is that it really points out just how complicated the fusion processes in deep down in the core of the sun really are. You sort of hear about the sun being, when you first learn about it, you hear about it as, well, you take some hydrogen and you fuse it together and you make helium, and that's basically it. That's what's going on. It's much more complicated than that, right?
It is. So what you're talking about there is the main source of energy in the sun, which mostly comes from, more than 90% of it comes from what we call a PP chain.
A PP chain. Now the P, so we've had C, N, and O, carbon, nitrogen, oxygen. P, I'm going to guess here, stands for proton?
That's right. Yeah.
Proton. Excellent.
So yeah, you might have seen the overview, the net reaction, if you like, of the fusion in our sun, which is generated by this PP chain. The net reaction is you shove some 4 protons together and you get a helium nucleus from that.
Right.
But the detail is actually really, really interesting. It's actually more than a 3-step process. So what you have is you've got these protons, and these are our charged particles that sit around in the nucleus of an atom when they're bound up into an atom.
Mm-hmm.
But in the sun's a plasma, so everything's kind of free.
It's just mingling around, yeah.
So you've got these protons mingling around. So step 1 is you have to take 2 of these protons and you have to bash them together. Now that sounds a lot easier than it actually is, because you've got 2 positive charges, and turns out that they don't really like each other all that much.
They don't. Like charges repel. And so 2 protons getting close to each other will push apart really, really, really hard, which means getting them to bash together hard enough to do something interesting with fusion is really hard, which is kind of why you need the temperatures and pressures at the core of the sun. Yeah,
so you need at least 4 million degrees to get to this kind of reaction to occur.
Right, so that's not mucking around. But you said a minute ago you need 4 of these things. It's a 3-step process. So that's just the first step.
So this step, when you put these 2 protons together, then you get this nucleus, which is created, which has got a neutron and a proton. So this is a heavy hydrogen nucleus, or a deuterium nucleus, right? So normal hydrogen just has a proton in the nucleus. This is heavy hydrogen with a proton and a neutron. And then you get some byproducts of that, which include a neutrino, for example. So then you got your heavy hydrogen. Step 2 is you take that heavy hydrogen. I mean, because let's imagine where we're trying to get to, right? You've got to start off with just protons, really, in the sun.
Mm-hmm.
And you've got to get them together to form helium. Now, helium's got 2 protons in its nucleus and 2 neutrons.
Right.
So that's the final where we're getting to, right? Now we've got to the point we've got 1 proton and 1 neutron. So if you smash that together with another proton, then you get, as you might expect, 2 protons and 1 neutron in your nucleus.
That's tritium. That's heavy Hydrogen.
Nope. You've gone the wrong way.
Oh, damn
so
it.
You've got helium now. You've got helium with 1 neutron.
Right. Okay.
Yeah. So it's light helium, if you like.
It's not heavy hydrogen, light helium. Okay.
Yeah. And so then once you've got this helium, then you can stick 2 of those heliums together. It sounds like you should just add another proton, but it turns out that that's not energetically very easy to do. What is much easier to do is stick 2 of these light heliums together, and then you get a normal helium nucleus with 2 protons, 2 neutrons, plus 2 leftover protons at the end.
Right. So it's a very long way to go to finally get to your standard common or garden variety helium nucleus. But, these reactions are going on constantly all the time. If you've got a bunch of protons and a bunch of protons and neutrons, a bunch of the deuterium flying around, and smaller but significant amounts of the light helium, eventually, right, you're going to get some helium formed. And you were saying that's sort of the backbone of the nuclear process. That's your PP chain.
Yeah, that's kind of your mainstream PP chain. There are some very slight variants on that, which are just detail, I think, really. But what's important is that whole chain process produces 2 neutrinos.
Okay.
And these are the things that we can observe, because we're not sticking things in the core of the sun, right?
No, we can't stick a little probe down in there and go, so what's going on? Let's measure it directly. All you can measure is what's coming out of it. And so we do that through looking at the neutrinos. So maybe it's time to just take a step in that direction and talk a little bit about neutrinos. Okay. Now, you said the very first step on that was you take 2 protons and you bash them together really, really hard at very high temperatures. And out of that, you get deuterium. And deuterium is a proton and a neutron. So 2 protons, proton and a neutron. Where'd the neutron come from? Where'd the proton go? Where'd the neutrino come from? Talk us through this one.
Right, okay, yeah. So what happens is you can imagine the second proton kind of transforms, and it actually transforms into kind of 3 different things. So it transforms into the neutron, but you have to conserve charge, right? You can't just get rid of this positive charge that's an aspect of a proton. You can't destroy charge.
That's a thing in the universe. Yeah. You have to hang on to the charge somewhere. So where does it go?
So in this case, the charge goes into a positron, which is a positive version of an electron.
I like the way you say that, a positron. It almost sounds like it's, some kind of bad guy in a 1980s animated kids cartoon. But anyway, the positron, yep. Positively charged electron thingy.
Yeah, so that goes winging its way back out into the plasma. Pretty much, it very quickly annihilates with another electron, and that's actually how you get the heat, the thermal energy from the sun.
Oh, okay. That's all coming from positrons and electrons annihilating each other, because that's what matter and antimatter do. They sort of disappear in a puff of photons. So that's cool. Okay. So that's where that goes. But you've got another thing. You've got a neutron, a positron, and
the leftover bit is this neutrino. And it really, these things are really like the leftover bits, and which is possibly why it took us a very, very long time to figure out what these things were. So if you look at kind of one fusion reaction produces actually not a lot of energy at all.
It's very small. Look, on the scale of the protons themselves, it's a modest amount of energy, but these things are very, very small, and so there's a bit there, but it's not very much.
So the whole reaction produces kind of less than I've got 10 to the minus 13 joules, a few tens of the minus 13 joules,
which by anyone's
a joule
language
is a really small.
Yeah, it's a really small amount of energy. Okay.
And then the neutrinos account for less than a tenth of that.
Right. But that's the interesting thing about the discovery of the neutrino, isn't it? That when back in the day when all of these processes were first being investigated, there was there was something missing. Something missing when you add up the energy of the things that went in and the things that went out of the nuclear process. There was just something missing there. It wasn't going to be charged because all the charge was accounted for. That was all figured out. So it needed to be neutral, but it had to be carrying away some of the energy. And it was hypothesized, go look for this really tiny thing. We'll call it a neutrino, tiny little neutral thing. And they found it.
Yeah. And it's really, if you're looking for an example of something that does not want to be found, we've got, putting aside our dark matter, dark energy, this is a particle that's in some ways it's ordinarily part of our normal standard model of physics, but it really doesn't like to be found.
It really doesn't.
So hard to detect.
It really doesn't. And that's for a couple of reasons. One is it's got no electric charge, so it's not going to interact through electric or magnetic fields. It's not interacting with light in a big way that normal matter does, which is full of electrons and protons. So it's not doing that. It's incredibly low in mass, so low that it took decades for people to even figure out whether or not it had any mass at all, or was it just completely massless. It's much, much lighter than the electron. It's this tiny, weeny little thing. And it only interacts through what we call the weak nuclear force, which by its very name is really weak. Like, it just happens so rarely. And so, it took a really long time to even figure out if these things actually exist.
So neutrinos, if you imagine that you're a neutrino and you look at an atom, atoms are mostly empty space. Right?
Yeah.
You've got this nucleus, which has the protons and neutrons, you've got an electron, but there's a huge amount of empty space there, right? It's just vast amounts. Now, we don't sort of, really notice this empty space because we have electromagnetic interactions between all sorts of stuff. So like it stopped me from, falling into this microphone. Then the electromagnetic interactions between the electrons in my face sort of interact with the ones in the microphone. And so, I don't fall through the microphone, right?
Exactly. You hear that phrase, atoms are empty space quite a lot. And that's, as you say, that's only true if you ignore the whole electromagnetism bit, because for all intents and purposes, the atom isn't empty because we see the effects of those electromagnetic fields. We get the push and the pull from the electrons and the protons throughout the entire atom. So it's not really empty in terms of interactions, unless you're a neutrino, in which case you don't see the electron very much at all. You don't see the electromagnetic fields. You just see this almost completely empty sphere.
So it just whizzes straight through atoms. Now, this is brilliant if you're trying to study the fusion reactions in the core of the sun, because it means that as soon as you produce a neutrino, that's it. It's flying, it's gone. It doesn't care that you're in the core of the sun, which is at several million degrees. It doesn't care that there's a whole lot of sun plasma to get through. It just whizzes straight out of the sun.
Yeah, like the sun's big, right?
Yeah.
So that's fantastic. The flip side to that coin is when you're trying to detect it on Earth, it just doesn't even see it. The neutrino wings its way through your detector, through you, through the entire planet, and continues on its way through the cosmos without even noticing. And that makes it hard.
It makes it very, very hard. So the way that we set up experiments in order to detect neutrinos are to look for some very rare interactions where, if you're very, very lucky, then your neutrino will come along, and instead of whizzing through kind of the empty space of an atom, it might just react or hit the nucleus of your atom.
Yeah.
And then some things might happen which you can actually use to detect that it was there.
Yeah, you've got to work with the stats, right? I mean, I actually had to just remind myself, because there's a classic in physics, there's the neutrinos interact so rarely that did you know that some ludicrous number of them are passing through your body every second, and you didn't even know that? And I just had to look it up. Do you know what the number is? The number of neutrinos passing through your body every second from the sun?
Yes, it is 60 billion through your thumbnail every second.
Yeah, 60 billion through an area the size of your thumbnail every second. Like, that's a lot every second. And occasionally, very occasionally throughout the year, throughout your lifetime, one will bounce off something in your body. So you just don't notice. So how do you detect one of these things? You've got to make a detector which is really, really big and really, really sensitive, and then be really, really patient, I guess.
Yeah. So what you want to happen is sort of one of these rogue neutrinos to interact with the material that you've got. Quite often people use water or ice or heavy kind of elements. In this case, the Berexino experiment uses hydrocarbons. I haven't gone into the detail, but I'm guessing that's just because they've got large chains with largish nuclei, carbon and things like that. Lots of opportunities to interact.
Yep.
And once you get an interaction, then you get this kind of flash of light, which is produced. So you want to then take your big sample of hydrocarbons in this case and look at it and see if you get a flash of light. Now, the problem
Just to be clear, before you go into the problem, I just want to paint the picture of what exactly we're talking about here. We are talking about an enormous tank. How big is this? How big is the balloon? I'm trying to look it up earlier.
So in this case, we're talking about a giant nylon balloon.
Giant nylon balloon.
Which has got hydrocarbons in it.
How giant? We should look that up. 'Cause it's
giant
really big.
is the size descriptor that I've got here. Without a measurement attached to that.
Okay, so you got this giant asterisk. Just imagine something really, really big. Balloon, nylon balloon.
I've got 278 tons.
278, okay. So a 278-ton nylon balloon of hydrocarbons surrounded by detectors, right? But this thing, it's not like sitting in someone's backyard. It's not up on the surface. It's down underground. Right? I've got that right, haven't I?
That's right. And that's where I was going to go, actually.
Okay, sorry. I did
the problem is, if you were to take this giant nylon balloon of 278 tons of hydrocarbons and just put it in your backyard, which would be a thing that you could do
yes,
if you,
yeah.
presuming you've got a nice large backyard.
Why not?
The problem is that the atmosphere produces lots of particles that interact in a very similar way. they're called muons, that interact in a similar way to how the neutrinos interact. So you just can't tell the difference if you've got a muon from the atmosphere or if you've got the reaction that a neutrino is produced in your balloon.
What you're saying is that because you're trying to measure such a rare event as a neutrino bashing into something inside your balloon, you need, like, the atmosphere is a very noisy place. The Earth is a very noisy place. There's stuff going on all the time. Where are the muons coming from?
So yeah, there's really high energy cosmic rays that come from space. So these are kind of photons and things that have been produced by supernova or intensely charged particles that are just whizzing through with huge amounts of energy. They crash into the atmosphere and these muons are produced.
Right. So the atmosphere is noisy. It's got stuff happening all over the place, and that's going to completely swamp any tiny signal that you might get from seeing the occasional actual neutrino. So you can't put it in your backyard. You've got to bury it underground to get far away from those atmospheric effects. So this particular experiment in Italy is about a mile down. Is that right?
Yeah. So underneath, and that protects you. So the muons would get stopped by all the rocks and sort of dirt and stuff like that. They get, they interact and they're gone. Whereas the neutrinos pass straight through.
Right. But wouldn't you, surely you'd still have contamination coming from the ground. I mean, the ground's full of stuff, right? And some of that stuff's going to be radioactive. I mean, there'd be a background.
I guess it depends on the energies as well. I mean, they do talk about how it's very easy to mistake a particular reaction of bismuth, in this case, bismuth 210. I don't know if it's your favourite bismuth, but...
Oh, yeah. I mean, it's one of the classics.
Basically, there's some of this in the nylon that the balloon's made out of, and that can very slowly decay, which produces a flash of light, effectively the similar reaction in the tank. And I love this story because so they figured out that this was happening, but there wasn't really any way which you could prevent this decay from happening.
Mm-hmm.
So what they did was very, very clever, was they managed to stabilize the whole system and keep it at such a very, very precise constant temperature that, yes, these kind of decays were going to happen from the nylon, but they were only going to happen right at the edges, so that the bismuth is kind of leaking a little bit into the balloon, but it doesn't get far, right? And it can't decay very far. So all you need to do...
It's not enough that you've got a giant nylon balloon a mile underground filled with tons of hydrocarbons, but let's keep it climate controlled to a really precise degree as well, just so that we can keep an eye on the bismuth interactions. This is a level of experimental detail that is off the charts.
It took, I think, about 4 years to get to that level of stability with the temperature controls.
They got a lot more patience than I've got. So this is the experiment, right? We're underground.
Yeah, so it's very clever because then you've got these bismuth things happening on the edges, but you can just ignore them, right? So if you get a detection right in the middle of your tank, now it's nothing to do with the bismuth.
Gotcha.
So I really like that solution.
It's
I
clever.
thought it was very, very nice.
Really nice.
Yeah.
Really nice. So that's what happens. Occasionally, you get a neutrino bashing into something inside your tank. It gives off a flash of light. You surround your balloon with photon detectors that can see that flash and go, hey, we might have just seen a neutrino and it was over here. And ideally, it was this much energy and so on. Somehow from that, you've got to work your way backwards to... So, what's happening in the core of the sun? And that's the next part of this story, really, isn't it? Because,
Yeah.
I mean, it's hard enough just getting to this point. It's hard enough even just detecting a neutrino at all, let alone figuring out, yep, so that tells us about the core of the sun.
Yes. So what you got to do is then look at the other reaction, the CNO cycle, which also produces neutrinos in the sun. Now, the CNO cycle is a little bit more complicated than the PP chain, which I'm sure you're pleased to hear. But I've done an abbreviated version, if you like, and I can talk you through that.
Okay.
So the CNO cycle, if you're a chemist, is kind of like a catalytic reaction where the carbon, the nitrogen, and the oxygen aren't actually important at all. I mean, they are, but
well, they're in the title. They're in the name. They must be important somehow.
Yeah, but they're not the things that are fusing. So remember, fusion is going from hydrogen to helium. But with a CNO cycle, all you're doing is using carbon, nitrogen, and oxygen to help you go from hydrogen to helium.
Ah, okay. So it's not about making carbon, nitrogen, and oxygen. Those have already been made through some other reaction. They're hanging around, but they're helping you to do this thing.
Yeah, that's right. So what you have is you have carbon 12. So that means you've got 12 items in your nucleus of carbon. And you stick a proton with that, and then you get nitrogen 13.
Okay.
Right, step 1. Step 2, your nitrogen 13 decays. It becomes carbon 13. Then your carbon 13 picks up another hydrogen, so it becomes nitrogen 14.
Right, so we're bouncing around between carbon and nitrogen here. Good.
Yep, so now you've got nitrogen 14. You add another proton to that one, and it becomes oxygen 15. Now, then your oxygen 15 decays back to nitrogen 15.
Okay, yeah.
We're nearly there. And then once you've got nitrogen 15, this is the good bit, because you can add a proton to nitrogen 15, and instead of going to, I don't know, something 16 or whatever, it actually goes to carbon 12, which is what we had at the start, plus helium 4. And helium 4 is the nucleus we're after.
Gotcha. So you start with carbon 12, right? Which is a very standard stable form of carbon. It's common vanilla carbon. And you just start throwing protons at it, and you build up these other isotopes of carbon and nitrogen and oxygen. But the punchline is that you get to a point where, well, we're just going to go back to carbon 12. But look, hey, left over, we've got helium nucleus, because the helium nucleus, 2 protons, 2 neutrons, is itself a very stable little lump. And so rather than going to, I don't know, oxygen 16 or whatever it might have been, it's like, nah, we'll be carbon 12 and this thing. And this thing is the helium. And you're back where you started. That's the cycle part.
Yeah.
Carbon, nitrogen, oxygen, and back to carbon 12 again. Very clever.
It is. Well, yeah, it's nice. Yeah, so once you got to carbon 12, you can start the whole process all over again. So, yeah, this is a really nice reaction. It's actually more efficient in producing energy than the PP chain is as well. The problem is that you need to have much, much higher temperature for this reaction to kind of switch on.
Right. And is that why you said it's much more important for bigger, hotter stars than our sun, but less so for the sun? Because it's just not hot enough?
Exactly.
Right.
Exactly. So the PP chain, you need 4 million degrees to get to fusion for that. For the CNO cycle, you need to get to 15 million.
Ooh, that is hot.
And the core of our sun, the very core, is only about 15.7 million Kelvin.
Right. So it can do it, but not much.
Yeah. But once you're a bigger, hotter star, then you're away. You're fine.
Yeah. No worries. So you said that in our sun, it accounts for what? Did you say about 1% of the...
Yeah,
of the total,
even less than 1%.
Less than 1% of all the fusion energy that's coming from the sun, which is not, it's not a big thing. But the CNO cycle's been known about for a very long time. It's been around for a really long time, yeah?
Yeah, since about the 1930s, I think. Yeah.
Right. Okay, so this was an established, we know that this is going on, but in terms of actually finding the experimental evidence for it, in terms of the neutrino output from the sun, that's only just happened.
That's right. Can I suggest a question that you might want to ask now?
Fire away. Knock yourself out. What should I be asking right now?
This was a question that I thought I don't know the answer to this, so I had to go and really think about it and work it out.
All right, hit me with it.
So the PP chain produces neutrinos.
Yeah.
And this produces neutrinos.
Yeah.
How do you tell which neutrino is which?
Funny you should mention that was actually down there on the list of my follow-up questions to all of this. I was going to let this all kind of settle out then and say, okay, so if it's really hard to detect a neutrino at all, how do you know which ones came from sticking protons together to make helium? And how do you know which ones came from the CNO cycle? That's ridiculous. It's not like they have labels on them. They don't come tagged. So, what do they have, different energies? How do you know?
Well, Okay, so I didn't actually know this. So I thought, well, I'd do what I'd normally do in this situation, which is go to the source.
Right.
Go to, in most situations, what we're talking about is a scientific journal paper, and I'd go and dig it out and, try and, blaze through all the big jargon and drill down into it.
See, that's what I love about you, Emily, is that you don't, this is, folks listening at home, this is not just Emily going and Googling something. I mean, it's not that simple. You've got to go and actually go back to the scientific literature. And she does that for you. Like, that's amazing. Well done, Emily. So,
Well,
so when
you'd be
you
more
went back
impressed
to,
now.
when you went back to the scientific literature on this one, what did you find?
Well, I went and looked at the original talk actually that was
Yep.
presented at this conference, and everything's online, which is nice, so I could go and look. And I looked at the slides.
Yep.
Because I'd probably be able to pick it up from the slides.
Sure.
Now, I'm not at all going to say anything about the science in terms of its validity, because I do think I've gone to a huge amount of effort to make this as properly established, and I've gone to a lot of statistical detail. There's a lot of really interesting stuff in there. But you might want to put on some sunglasses before you look at these slides.
Okay. Bit bright, are they? Bit loud?
Yeah, I mean, there is a kind of a known thing that scientists are not always the best at producing PowerPoints.
Is there a bit of Comic Sans involved? Have we got some bad font choices?
Not quite, but there were about 17 different plots and about 100 million different colours highlighted.
Ouch. Okay, so
it was a rainbow.
graphic design considerations aside, what did we find out?
So what I found out is actually not that you look at an individual neutrino, which kind of makes sense.
Yeah, I guess.
Every detection has uncertainty associated with it, and so on and so forth. But what you look at is you look at the bulk properties of all the neutrinos that you've detected.
Okay.
So, and what's that? Is you look at the energies of the neutrinos that you've found, and so it's like an energy spectrum. So instead of a spectrum in different colors of light, you have a spectrum of different energies of neutrinos. And from this energy spectrum, what you find is the energy spectrum from the CNO cycle. It's pretty similar to that of the PP chain, except it's just a little bit different in shape, and particularly it goes a little bit higher, slightly higher energies.
So this is where the theoretical physicists are really earning their keep, right? Because they're able to look at it and say, okay, all right, we can figure out from how these things are happening and the conditions that we believe or have measured to be down in the core of the sun, we can figure out what the energy profile, what the distribution of energies of these neutrinos should be. It should look like this. And with any luck, that'll be sufficiently different for the PP chain and for the CNO cycle that we'd be able to tell them apart if we measured enough neutrinos. Is that the idea?
Yeah, exactly.
Right.
And what they've even got there is also they've got the spectrum of the bismuth decay that's going on, and also, considering that. And even with all these put together, then they've got a very statistically significant detection of these slightly different energy spectrum neutrinos.
Right. So it's not just looking at any given neutrino and saying that one there, that one came from the CNO, whereas that one came from the PP chain. No, it's overall, can we see enough of these neutrinos? But how do you... Oh, now my head's hurting. How do you separate them out? I guess what you'd have to do is you'd have to say, all right, if we assume that you've got roughly this many neutrinos coming from this process and this many neutrinos coming from this process, and the two processes have these different kinds of energy distributions, then the overall distribution would have to look like this. And I guess maybe it might have, a couple of bumps to it or be spread out in a particular way. But you'd be able to tell.
Yeah.
You'd be able to tell if the CNO cycle was missing from that. And it's not. It's there.
Yeah. This is pretty common, actually, in science, where it's very difficult sometimes to make a measurement of something completely independent of all the other effects that are going on. And this is true in pretty much all the sciences, actually.
Yeah.
There's always some background. There's always some other effects that you wish weren't there. So it's very, very common to have, let's say you've made a graph of your all the different energies of neutrinos, in this case, that you've measured. But you know that there are contributions from these ones, there are contributions from these ones, there's contributions from background, there's contributions from bismuth, and so it's actually a very normal problem to have to then separate those out and say, okay, well, the stuff at this high end, that's mostly dominated by this different process. The stuff at the low end is dominated by this process. And so it's almost like sticking together lots of different graphs to make the graph that you've observed.
Yeah. Yeah. And the point is that you can tell the difference between, is the thing that I'm interested in there or not? I mean, one of the real classics in the last decade or so was the discovery of the Higgs boson, where you've got particles being bashed together in the Large Hadron Collider over in CERN, and you've got ludicrous numbers of these things. I mean, the stats on the Large Hadron Collider is just off the charts. You've got countless numbers of these things, and the detections where there's an actual Higgs boson involved is tiny. There's hardly any of them. But if you build up enough of them over time, then you've got this big background of all sorts of particles being created, doing crazy things. And then this tiny little bump, which is there because the Higgs showed up. And out of this enormous number of events, just this tiny little bit, which is that one, that bit there. If the Higgs wasn't around, that bit wouldn't be there. And it's statistically just extraordinary. This is another version of that, I guess.
Yeah, exactly.
Okay, so pulling ourselves back around then to the heart of this story. Let's recap. We've got a process going on at less than the 1% level in our local star, but is really important for big hot stars across the universe. It's the CNO cycle. We know that it's got to be there, but we finally found the signature for it in the neutrinos that are coming from our sun. And so that's the exciting part about this. That's the exciting experimental part about this. We did that by burying an enormous balloon of hydrocarbons a mile underground in Italy and sifting through all of the stuff that we saw coming from the reactions in that balloon for the neutrinos. And we were able to see the signature of the CNO cycle in those neutrinos. So that's all great. But Emily, so where does that leave us? What do we take home from all of this? What have we got at the end of all of this effort?
All right. Well, the first thing is it's obvious that this is really useful for the study of hot stars, right? So you can extrapolate from even just a few percent of our sun and then say, oh, hey, this thing does actually exist. I mean, this is the first time we've directly observed the CNO cycle experimentally. So that's cool.
Yeah. I mean, you can't directly observe it from any of the really hot stars that you assume it's going on, like the clappers across the other side of the galaxy, because we're not near those stars. I'm assuming you can't observe it directly.
No, but it's interesting that we could now use this, kind of techniques with them, enhancements in technology, new detectors and so on. Potentially we might be able to pick up neutrinos from these other stars. Who knows? On a different note, even for our sun, we can actually start to think about what particularly is the metallicity of the core of the sun.
The metallicity.
Yes.
What does that mean?
Now, remember that for astronomers, metallicity, or the metallicity is an amount of metal. And for an astronomer, a metal is anything.
Metal with a big asterisk. Correct me if I'm wrong. Metal for an astronomer is everything that isn't hydrogen or helium, right? Is that right?
Yeah, exactly.
Yeah.
Exactly. So carbon, nitrogen, and oxygen are metals for astronomers.
Yeah, it's all metals.
And so the overall, amount of metals that you have is important because, it tells you things about the evolution of the entire galaxy. How many different generations of stars have gone before our sun. So we'd like to know what the metallicity of the sun is in the core. We suspect that it might be similar to what it is on the surface. We can measure it on the surface in excruciating detail. It's beautiful detail, but we can't measure it directly from the core apart from through these kind of reactions. So it's very nice. Although it's interesting that these measurements suggest that the metallicity is pretty similar between the core and the surface. There's also some competing ideas that come out recently, or some competing measurements that say it might even be a bit higher in the core than it is in the surface. So there's some work to be done there.
But so these measurements are allowing us to understand more about, because they directly involve some of the metals, some of the big metals, the carbon, the nitrogen, and the oxygen. It's a way of actually probing. So how much of this stuff is actually there to more detail than we've been able to do before?
Yeah, and also these kind of things are important, even for very civil purposes. Everyone knows that we're trying to recreate fusion here on Earth, trying to create the sort of core of the sun. Now we're trying to do that through the PP chain, or a similar kind of set of reactions to the PP chain. But it's not, and that's difficult enough. Let's not downplay those enormous efforts. We'll get there, I think. It's getting there.
But it's a hard problem.
It's very, very hard. But wouldn't it be better one day to be able to do CNO fusion, if that's even more efficient? Once we've got our, deuterium fusion all set up and working, then we're happy and we're producing huge amounts of energy. We may want to look to CNO as the next level of fusion, being more efficient.
It's an intriguing idea, isn't it? Because, I mean, as you said, the CNO, the carbon, the nitrogen and oxygen, they're basically catalysts in this. They're just along for the ride, and it's the fusion of the hydrogen into the helium that is ultimately the payoff there.
Yeah, you just got to do kind of 10 million degrees hotter, but
piece of cake.
How can it be?
Come on, fusion theorists, what are you waiting for? Get at it.
Yeah, so I think it's my final point of the so what, if you like, is it's actually a quote that was in the original Nature report on this announcement, is that the quote is, "It's intellectually beautiful to actually confirm predictions of stellar structure theory."
I mean, I think that's a fair statement. Intellectually beautiful. Another way of saying that is, I can't believe it's taken so long to actually be able to confirm this. But I guess stepping back from that a little bit, is science or theory without experimental confirmation is incomplete. We're not there yet. The whole beauty and utility of science is about confirming the ideas that you had in the first place. And so this is a really, really nice moment of being able to say, here's an idea that's been around, you said earlier, since the 1930s, and we were pretty sure it was there, but it's a really, really hard thing to probe.
Yeah.
It's neutrinos, for goodness sake. This is hard.
And what I think, so this is a quote from Mark Pisano, who is actually a friend of mine, which is why it sort of jumped out at me as well. So I think what he's also trying to say there is that, so often in science, you produce a theory, and even if it takes you 100 years to go out and get the observations, it's pretty rare that those observations just say, "Yep, theory's good, carry on."
That's true.
So sometimes it's nice to just say, "Yep, that works. We've got it right. Cool. We can carry on with some of the other questions that we have."
Well, that does indeed bring us to the end of another episode of the Syzygy podcast. Emily, that was a nice little moment to end on there. That sometimes the universe throws us a bone and says, "You know what? You've been working hard. Here's your reward. That idea you had, yep, it's good. Carry on. Keep doing the thing that you're doing." It's a nice moment.
And yeah, and when I think about lots of my research, I'm carrying around, half a dozen stars that every time I do some new observations on them, they appear to be doing something weird and wonderful, but then it's something differently weird and wonderful to what they were doing 10 minutes ago. And you think, really? Can you just calm down and just behave for 10 minutes? I know it's interesting what you're doing, but sometimes it's not interesting, can be useful too.
Could you just let me nail down one thing? And I guess that's what the universe has done for us on this one. It's like, okay, all right. CNO cycle, you can have that one, right? Draw a line under that one and let's move on. Speaking of drawing a line under it and moving on, we're going to find our way out of this episode. Emily, if people wanted to contact us and talk to us about their favourite neutrino observation, or indeed any other thing in the universe of astronomy, how could people possibly get in touch with us? What would they do?
So, if you're a tweeter, I'm quite into the birds in my backyard, and I tweet at them. But if you're tweeting on the internet as well, then you can choose
Lockdown's really getting to you, isn't it, Emily?
It's a bit. You can compose your tweet to us at SyzygyPod, SYZYGYPOD.
That's right.
Oof, nearly lost that one halfway through.
Other places on the interwebs as well. We are on the Instagrams and we are on the Facebook, all at SyzygyPod. That's where you can find us. We also have a website, don't we?
We do, syzygy.fm. And that's where you can see lovely show notes. You'll be able to go and look at some very, very nice PowerPoints from the Berexino team if you're into, if you need a bit of colour injection in your life today, I would think.
It sounds like it. Just as Emily said, put your sunglasses on first. And at our website, syzygy.fm, there is a contact page. You can get in touch with us if Twitter or Instagram aren't your thing. Send us through a note, and you never know, we might feature your query or your comment on a future episode. If you want to support the show, there's a bunch of ways you can do that. You can just tell everyone you know. Think of that person in your life who would get a kick out of discussing astronomical things, and tell them you should go and listen to the Syzygy podcast. And that helps us to grow and build up our audience. The other thing you can do is you can go to our Patreon page. Go and become a patron of the show at patreon.com/ you guessed it, SyzygyPod. And you can sign up to be a financial supporter of the show. And all of the money that we get, the huge amounts of not terribly much money at all that we get through Patreon, help us to keep the electrons flowing through the website and help us to do every once in a while something like a live festival show when festivals once again become a thing in this strange new world. Otherwise, let's wrap it up there. Emily, I'll catch up with you in a week or so for another edition of the podcast. But until then, stay safe, and I'll catch you later.
See you later.
Bye, everybody. Every once in a while, the universe just goes, yep, got that one right. Next.
Not as often as you hope. So it is, I guess, must be a great sense of satisfaction. It's just like, yes. And I'm sure the people doing the Higgs boson, for example, also got that. They're just like, good, nice.
Yeah, although the Higgs boson is a weird one, because there was also a palpable sense of, because we were really kind of hoping for something a bit more, like this is the simplest version and it doesn't solve a whole bunch of problems that are now still there. If it had been more complicated, we would have had something to chew on. But no, you're just going to give us that and then walk away whistling? That's the best you can do? Oh, well, it was almost like the universe was trolling us.